All right, Susie, would you please introduce Dr. Noel?
Well, I would first like to say to Betsy Kazazian, thank you for organizing a wonderful luncheon, which we did not get to have, but I hope that I get to work with you more in the future and in person. So this was kind of a happy, sad thing, but I am really excited about Dr. Alexis Noel. I saw her on CBS Sunday Morning. How many years ago? I don't remember, but I've been bragging about her to all of our ARCS friends ever since then. And we are just really excited to have Dr. Noel speak to us about all of the interesting things that she's doing. She is a research engineer at the Georgia Tech Research Institute's Aerospace, Transportation, and Advanced Systems Laboratory, or ATAS. Dr. Noel received her doctorate in May 2018 at Georgia Tech, where she specialized in biomechanics with a particular focus on biological mechanisms. Her work on frog tongues, cat tongues, and earwax was highlighted in the media outlets like NPR, the New York Times, Science Magazine, and the Discovery Channel. During her time at GTRI, Dr. Noel continues to research bio-inspired adhesive systems with direct application to grip in wet, biofouled environments. In addition to biomechanics, she also pursues research in additive manufacturing, soft robotic actuation, and Baptic feedback for mixed reality platforms. Dr. Noel is an author on 3 U.S. provisional patents from bio-inspired microfluidic dispensing technology to methods for processing biological waste. I have to tell you, I spent an afternoon with a dictionary before giving this introduction and learning what all these things mean. So we are so fortunate to have people like Dr. Noel in this world. And for people like us who only raise money for people like you, Dr. Noel, I am very, very grateful that you are doing what you are doing. She will answer questions afterwards if you want to type it into the chat or raise your hand when she's finished speaking. Dr. Noel, unmute yourself and tell us what you're doing.
Hi, everyone. Can you hear me?
Yes.
Can everyone hear? Great. Thank you so much for inviting me to give a talk today. As she mentioned, my name is Alexis. I work at the Georgia Tech Research Institute, and I do all manner of weird, disgusting research. So I actually have been at Georgia Tech for all of my academic life. I did my doctorate in mechanical engineering, studying biomechanics. My thesis was on animal tongues, so I'm going to be talking a little bit about that today. My new work has started to diverge just a little bit. So I'm working on a few different projects. I'm going to be talking a little bit about one of them today after I talk about tongues. So I am currently working on some biomedical applications using some of the biomechanics work that I've been working on for the past couple of years. I'm also been working on a Bill and Melinda Gates Foundation program to reinvent a third world toilet. So if anyone has any toilet related questions at the end, I'm also happy to answer some questions about that. So let me see if I can get my screen share to work. Okay. And okay, great. Can you all see my screen? Okay.
Yes.
Excellent. Hopefully it's not the one with the notes on it. Okay. Great. So today I'm going to be talking a little bit about my frog work, my frog tongue work, my cat tongue work, and then I'll give you all a little sneak preview of some of the virtual reality work that I've been doing. And if we have any additional time, I can also show some slides about working with river otters. Those are always very cute images. Great. So I'm going to start off by talking a little bit about why I was interested in this field in the first place. For many years, I've been really fascinated by soft robotic systems, and I'm sure a lot of you have seen some of these fun news articles that have popped up over the past decade of entirely soft robots able to grip and grab onto other soft objects. Very applicable for the agricultural areas of, say, grabbing a peach off of a tree, or even some underwater grip areas like you see here in this octopus tentacle. They're starting to create octopus-like arms. One thing I noticed was that all of these entirely soft robots use pressure with frictional forces to be able to grip objects. One thing that you'll notice when looking at the biological world is that a lot of soft tissues will actually have different types of surface structures to help with passive grip. So I was very interested in how we could use different types of fluids or different types of microstructures to be able to passively grip onto objects, and how we can apply that to the soft robotic domain. And tongues was a fantastic place to start. So like I said, my thesis was on animal tongues. I was actually inspired, I actually owned a chameleon. That was one of my very first animals. And I was inspired by the chameleon tongue, which is able to stretch to 3 to 4 times its length in a fraction of a second and grip onto all sorts of different insects. So as you can see here in the top left image, here's a chameleon tongue grabbing onto an insect prey. I was also fascinated with some of these other tongues, like cat tongues. I'm sure if you've ever had a cat lick your face, it's very rough, very scaly. So I wanted to explore that area. And there's also a variety of different tongues in the biological world that have a whole bunch of different uses. So you can see in the top right, you have gecko tongues that are designed to help clean their eyeballs. In the bottom left, you have bat tongues that actually create these little fans to help grab onto nectar when they're eating. And then you have other tongues like our tongues, which are highly tuned to be able to taste and manipulate foods in our mouths. And even giraffes have these long, very muscular tongues to help rip leaves off of branches or grab objects. So I wanted to hone in on amphibian tongues to start. So let's see if this slide will load. Aha, excellent. So what you see here is they're called Pac-Man frogs. They look like Pac-Man. Cute name. So Pac-Man frogs are able to grab onto just about any sort of surface using their very sticky tongue. So they can grip onto slimy surfaces like other frogs. They can grip onto hairy and furry and feathery objects with their tongues. And it doesn't seem to matter what the substrate is. Their sticky tongue can grab onto it with no slip. And that's a pretty fascinating object to explore, just because a lot of robotic systems that you'll see have difficulty gripping onto slippery, slimy, dusty objects. So we wanted to see what we could learn from looking specifically at the frog tongue. So the first thing we did in the biomechanics world is you take some high-speed footage of the object of interest, which is, we did the leopard frog Ranapipians. This video is slowed down 56 times, so you can really see the kinematics of the tongue as it unfolds and impacts onto the insect. And we found some very interesting things. We found that the frog can capture prey in under 0.07 seconds, much faster than you can blink. And these insects actually feel some relatively significant impact forces. So we tried to break down the problem into 2 different sections. We wanted to look at the tongue tissue itself. We also wanted to look at the saliva and then see how those 2 could lead to prey capture. So if you zoom into the surface of a frog tongue, it's actually quite fascinating. It looks very different than our own human tongue. The frog tongue actually looks like a toothbrush. If you zoom in very, very close, they have these tall spindly structures called papillae. And the papillae are about 100 microns tall, so about the thickness of a human hair, and they're covered in them, absolutely covered in them. And what's really interesting about this is that the saliva that they secrete is actually secreted through the tongue surface itself. not through any sort of salival glands like what humans have around the surface of their mouth. So what this means is that frog tongues can actually create a hydrogel-like substance or on the surface of their tongue. So very much like Jell-O, where you have something very soft, a soft solid kind of infused with this very sticky saliva. So as the tongue impacts the insect, it's able to regenerate that saliva and keep a continuously moist tongue. We also found that the tongues are extremely soft. They're about as soft as chewing gum as a reference. I know this from poking many a frog tongue. So we actually collaborated with the Amphibian Society, which is, I believe it's over in Decatur now. They had a whole bunch of frozen frogs, a variety of different exotic frogs, and we measured the tongue tissue softness for all of them. Of course, these are ex vivo, and we found that they all were about the same in terms of softness. So what does that mean? Why is softness important? Well, when we take an indenter, tiny little metal indenter about, I don't know, 4 millimeters in diameter, and you put it on the surface of frog tongue and you pull up, you'll find that the tongue tissue itself deforms before you get any sort of splitting to occur within the saliva. So this means that the tongue actually takes in a lot of that energy for deformation and makes sure to grip onto the surface as much as it possibly can. So what you see here in the middle is some data where you have the force of adhesion, or the force that's being applied to the indenter, versus the displacement on the x-axis. And all the way up to about 5 millimeters of displacement, the tongue doesn't peel from the surface at all. And it's only at about 5 millimeters that you start to have enough force that the saliva itself splits, and that's when you start to get this peeling action. This is very, very different from our own tongues. So if you did the exact same experiment on your own tongue, the saliva, your tongue is stiff enough that it wouldn't deform very much at all, and the saliva would split and separate, and you wouldn't be able to grab nearly as much as a frog tongue would. And so we also did a fun little visualization where we created a transparent indenter, so you can actually see the tongue splitting and separating from this indenter here as it goes. And you can see these tiny little threads of saliva that are splitting over time. Now, the frog saliva, this was a very challenging experiment that we had to do. We actually had to scrape about 16 to 18 frog tongues in order to get enough saliva to do some testing. And what we found was that the saliva exhibits both elastic and viscous properties. So what does that mean? So it acts very much like a spring. It's very springy. And you can notice this springiness through these rib-like shapes that you see when you have a sample of saliva and you separate it between two plates. So it wants to bounce back. And it also has viscous properties. So it provides a damping during impact. And so you're going to see the importance of those two aspects here in a moment. And on the far right, this is actually a machine that I built early in my doctorate to measure frog saliva. It's a portable extensional rheometer. So you can actually pick this thing up and take it out to the field if you actually got some saliva on hand. So a fun little trip I took was to go over to the San Diego Zoo, and I actually put anteater saliva inside of this machine and measured the viscosity of anteater saliva. A very unique experience of having an anteater tongue like all over your hands. All right. Okay, so how does the frog saliva work to grip things? So this is a fun experiment that you can do with middle schoolers to show how the viscosity of fluid is able to grip objects. So in this experiment, you have a brick, you have a piece of wood with a handle, and then you put fluid in between the two surfaces. So in this first video, you have a layer of water, which has very, very low viscosity, very similar to human saliva. Human saliva is very much like water. In the middle, you have honey, which is a lot more viscous. It's very thick. Then you have jelly on the far right, which is very, very viscous. And frog saliva is somewhere in between the two. So when you put the thin layer of fluid in between them and you try and separate it, the faster you try and separate it, the more weight you can actually pull up. So you'll notice in these videos, the faster the undergrad pulled the handle on the brick, the more weight they're actually able to pick up. The slower you go, the more likely it is that it's going to separate. So this very simple experiment actually illustrates how the frog tongue is able to grab onto all of these really challenging surfaces with just the use of its viscous saliva. And this principle is called Stefan adhesion, where you have 2 plates with a very thin layer of fluid, and it's velocity separation based. So the faster you go, the more force it takes to separate those 2 plates. And what's really fascinating about frog saliva is that it can actually change its viscosity based on how much shear is exhibited within the layer. And so this actually helps them grab their prey and then also remove the prey inside their mouth once they've captured it. When the tongue impacts the insect, the saliva becomes very thin and very watery, very much like our own saliva. So that saliva is able to flow and penetrate all of the cracks of the insect and increase that surface contact. And then as the tongue is pulling back, it actually, the saliva viscosity changes and it becomes very thick, very much like honey, and it grabs on using this Stefan adhesion mechanism. So this is a very, very high level summary of how frogs are able to grab onto all sorts of interesting surfaces. During impact, it flows and increases surface adhesion. And then as it pulls back, it grips using that Stefan adhesion principle with high viscosity. And then the tongue, the very, very soft gum-like tongue, is able to store that energy through deformation, delaying saliva peeling. Okay, I'm happy to take questions about frogs now, or we can also just do questions at the very end. All right, well, we can do questions at the end. All right, so I'm gonna pop on over to the next project that I did during my doctorate, which was looking at cat grooming. Cats are my favorite animal, so I was very thrilled to be able to pursue this topic. And what we were interested in was the cat tongue itself and how these sharp barbs on the cat tongue, A, what are they used for, and B, why are they shaped the way they're shaped? So, you know, regardless of what feline you're looking at, all felines groom, from house cats to snow leopards to tigers, and they all have this rough tongue. So why do they groom, and what does that tongue look like? So cats spend nearly 25% of their waking hours grooming, and they groom to remove loose fur, to remove odors, for relaxation and blood circulation, cat-to-cat bonding. They also use their tongues to help with thermoregulation. So this is a photo of a cat paw right after grooming. And just by licking the surface with saliva, it's able to drop its body temperature down by about 30 degrees Fahrenheit. So the distribution of saliva into its fur helps with thermoregulation. And we actually characterized the different parts of the grooming lick. So this is a video. I put flour on a cat and videoed it grooming itself and cleaning itself. This is sped up about 2 times, and you can see that the cat is relatively efficient at removing that flour from the surface of its fur. And so during this video, you can see that the tongue extends out of its mouth and compresses down onto the fur. We call that phase extension. Next, it expands. It actually stiffens its tongue and causes those little spines on its tongue to spread out and go vertical. The next phase is the sweeping motion, where it licks and pulls its tongue back into its mouth, dragging those spines through its fur. And then lastly, it retracts its tongue back into its mouth by curling its tongue slightly so the spines don't stick on its lips, and pulls any sort of fur and debris back into its mouth. And this phase takes about 1/4 of a second, so it's very quick. And so this mechanism can be found across all different types of felines. And we had the wonderful opportunity to get a variety of tongue samples from Zoo Atlanta, the University of Tennessee, in the Institute of Agriculture. They work with Tiger Haven, which is up in Tennessee. Tiger Haven is a place where they take in exotic animals that people think they can have as pets and soon find out that they cannot. So they rescue those animals and give them a happy life. But unfortunately, some of those animals don't live very long after being cared for by humans, by pet owners. And so they actually do save tissue samples for research purposes. And that's where we were able to get a lot of our tongue samples. And we also explored some different taxidermy studios around the Atlanta area. So we were able to get a bobcat and cougar tongue from there. So we had 6 different types of feline tongues, and these are all relatively to scale, from cat all the way up to lion. And so what we found, and so you'll notice looking at these images that all of them seem to have these barbs on the surface of the tongue. So we wanted to take a closer look at these barbs. So we did a CT scan of what you see here is a cat tongue. And so in the back third near the throat, the third of the cat tongue, these are actually very small, very soft pili. They feel like even softer than toothbrush spines. They're very soft and deformable. And in the front 2/3 of the tongue, you have these large rigid papillae. They're very rigid. They're keratinized structures. So they feel like your fingernails. And you have a good array of them. So during the literature search of cat tongues, there were not that many papers on cat tongues. What everybody had concluded was that the spines on the surface of the tongue, the first 2/3 of the spines were conical. And you can see in numerous papers, everybody says that they're conical. Well, one of the interesting things that I found is that when I looked at the cat tongue from the opposite direction, the spine is in fact not conical, but actually scoop shaped. So they look like tiny little ice cream scoops. And this is true across any feline that you may look at. So why are these spines shaped like little ice cream scoops? What's the purpose? And so we pulled papillae from each one of the tongue samples that we had. And what's fascinating is that these papillae are the exact same size and shape regardless of cat. So your domestic house cat spine, tongue spine, is the exact same size and shape as your lion spine. The lion just has more of them. So they're same length, same density. It was very, very strange. So why are they all the same size and shape? So what we hypothesized was that these little spines would actually hold fluid, very similar to a coffee straw. If you dip a coffee straw into your coffee, you'll see the coffee wick up using capillary action. What we believed was that these spines will hold saliva, and when the cat goes to groom itself, it's able to distribute that saliva deep within its fur to provide more cleaning action. And so we were able to characterize this flow. You can see on the bottom left, you have a cat spine that is wicking up red food dye. And from a different angle, you have a tiger spine shot at about, it's slowed down about 3 times. And so it's actually, you can see it pulling in this orange food coloring deep into its cavity and holding that fluid there. So your standard house cat can hold about 6 microliters, which really isn't that much. It's a fraction of a teaspoon of fluid. Tiger can hold more because it has more of these spines. And so what does it do with this saliva? Well, now that it holds the saliva within its tongue, it needs to distribute the saliva within its dense fur. So do you remember that the few different steps of cat grooming? One of the steps was actually stiffening of the tongue so that the spines pop out. So you can actually notice in the relaxed state, the spines are about 30 to 45 degrees angular to the surface of the tongue. But once it stiffens, the spines actually pop out to about 90 degrees. So the reason that it does this is that it needs to be able to take these fluid-filled spines and penetrate down to the layer of the skin to be able to distribute this cleansing saliva down to its undercoat. And the thing that it's fighting with, and I tried to summarize this here, the thing that it's fighting with is that that when you wet hairs, they actually tend to clump together. So when you get out of the shower and you look at your hair, you'll notice that your hair clumps into individual bundles of hair. And so the surface tension of the water will actually pull all of those hairs together into a minimum porosity, dense clump of hair. So the way I like to describe it is, if cats didn't have spines, if cat tongues were like dog tongues, they were just coated in saliva and they went to groom their fur, they would only be able to wet the top fraction of their fur surface. So you can see in this image here on the right, bottom right, when you wet this top surface, hair will clump together to a minimum porosity of about 0.09, meaning that there's very little air or space between the hairs. But due to Darcy's capillary model for wicking, that saliva would actually never penetrate the hairs underneath. So if you had a dog tongue filled with saliva and you wiped it over the surface of some fur, it would only ever penetrate about 0.5 millimeter of fur and leave the other portion of dry hair completely untouched. So in order to be able to wet that fur underneath that top clumped layer, you need to have penetrative spines that are able to go all the way to the surface of the skin and spread that saliva. So you can see in the middle here, we put some blue food dye inside of a cat papilla, and then we drug it through some fur, and you can see that the saliva is able to distribute relatively evenly through that area of contact. A fun adventure that I had near the end of my doctorate was that I got the opportunity to go up to Harvard and go to their, they have a library full of animal parts. It's in a basement. It's like a couple acres of animal parts, all dating all the way back to like the 17 and 1800s. They even have components of whale specimens, which is amazing. But a really cool thing is that they had drawers upon drawers of cat fur, of taxidermied cat fur that people were able to collect from some of these hunting expeditions from a very, very long time ago. So I was able to look at all of these fur specimens and be able to characterize different properties like fur density, hair radius, and hair length to look at whether the fur properties would change the way that the saliva is able to be distributed through the fur, and really understand why all of these cats have the exact same spine on the surface of their tongue. So I got to measure things from leopards to bobcats to even those very fluffy Persian cats that some people may have, very large fluff balls. And this is probably one of my favorite figures that I've ever made, ever. On the far right here, it's actually a plot of showing why most animals, most cats are able to groom themselves and why some cats are completely ungroomable. So on the y-axis, you have the so when you have a whole bunch of fur and you compress it, there's a maximum depth that you can compress it to based on how much fur there is and the size of the fur itself. That's called the height of the fur. So in this figure here, you can see these yellow circles are the individual hairs, and this top surface is the tongue, and then you have the papillae here in the middle, and then the skin is on the bottom. And there's actually, based on the highest density lattice arrangement of circles, you can actually calculate what the maximum compression height would be for certain types of animals. So you can imagine more fluffy animals are not going to be able to compress as far as, say, animals with very thin fur like a cheetah, which can compress very, very thinly. So based on that compression height of the fur and the height of the papillae, which is identical regardless of cat, there's actually a cutoff limit for groomable versus ungroomable cats. So you have all of your standard cats, your bobcat, tiger, leopard, and a lot of your standard short hair cat varieties are all considered groomable because their papillae can reach all the way down to their skin. Some of these other more exotic breeds of cat that have been bred over many, many years to have certain distinct coats of fur, have difficulty actually grooming themselves because their little spines on their tongue cannot actually penetrate through all of those layers of fur to get to the skin. So they have much more, they have a lot more issues with clumping of hair, and you need to be very, very certain to groom them constantly. So, and to kind of wrap up the program, we actually looked at, could we actually mimic some of these interesting grooming mechanics of the cat tongue to create our own cat tongue mimic. So what you see on the top here is a slice of an actual cat tongue with the spines highlighted in this green UV dye, and how the spines actually curl as the tongue curls. And on the bottom here, I actually created a 3D printed mimic using silicon and some resin-based 3D printing techniques to create a fake cat tongue. And so we have actually, another interesting part of this fake cat tongue is its anisotropic spine. It makes it very easy to actually remove hairs from the surface, unlike a standard hairbrush. I'm sure all of you know the pain of having to remove hair from a hairbrush. It's very challenging, but a single swipe of the finger across this cat tongue hairbrush, you're able to remove all of the hair. So we've actually been approached by a few different groups like L'Oreal and even Speedo at using some of this technology to be able to grip onto different hairs or even be able to distribute fluids like mascara. So that work is still ongoing. So in summary, for the cat work, the papillae length is ideal for penetrating through a variety of different types of furs. The spines on the cat tongue are identical, regardless of what cat species you're looking at. And this unique scoop shape that's found on these papillae helps wick up saliva and then distribute saliva down to that undercoat. Okay, and then the last topic I wanted to talk about is a lot of ongoing work that I've been doing recently. I took a left turn into virtual reality. I was very inspired by virtual reality a number of years ago. I thought it was the coolest thing since sliced bread. So I really wanted to get into that area and see how my biomechanics background could be applied to help further this field. And so this was a collaborative project that I did with some on-campus members, as well as the Children's Healthcare of Atlanta, looking at how we could use some biomechanics principles to create a haptic feedback glove for virtual reality to help with some rehabilitation needs for children with cerebral palsy. It's a bit of a mouthful. So I'll explain what haptic feedback is and what virtual reality is for anybody who has not experienced that yet, and where we are now. So the goal of our project was to look at assisting pediatric patients that have cerebral palsy in opening and closing their hand, which is actually a very challenging mechanic that you have to do as a child with CP, to be able to grab things that can be impactful, from like putting on clothes to opening doorknobs. And so we really wanted to find a fun and immersive way to help train that muscle memory in their fingers to help them open up their fists and be able to conduct pediatric clinical trials to explore the use of some of these cutting edge technologies. So we wanted to provide a fun, immersive experience, translate a lot of known assessments into this virtual environment, and then track the growth over time. So for those who are unfamiliar with virtual reality has really transformed the world of video gaming, if you all are familiar with that. So it really takes a 2D screen and provides a 360 visual using this heads-on display that you can see here in the top left. And using a variety of different controllers, you're able to interact with this 3D world around you. And over the past couple of years, VR technology has really taken off in terms of affordability and visual performance. But little effort has been made on trying to bring in some of the other senses into the virtual world. Some of the other examples of more immersive experiences are things like the Infinideck, where you can actually walk infinitely into a virtual world, and the Tesla suit, which will be able to actually track the motion of your limbs and provide some haptic feedback. Haptics being touch, so things like vibration, sensitivity, being able to feel forces on your hand is the area that I'm very interested in. So I wanted to see how we could bring the ability of touch into the virtual world using some of these soft robotic mechanisms. So why did we decide to look at assisting children with cerebral palsy? So, cerebral palsy is a leading cause of childhood disability, which causes upper limb impairment, which makes it very challenging for bimanual task and digit coordination. And this can make it challenging for play and daily activities. And being able to help with upper limb impairment can help increase quality of life for these children. A lot of the therapeutic interventions that are being done right now involve these very large, very bulky orthotic technologies. Some of these technologies are also being used for stroke patients to help with digit manipulation. We wanted something that was a little less bulky that can be put on to the arm of a child to help them with the motion of opening and closing their fist. And one of the key things that we wanted to do was to help translate this PEG experiment that you can see in the right-hand side of the screen, where the child goes, picks up a peg and moves it to another peg and places it, and trying to translate that actual physical task into the virtual world and make it a little more engaging. And so this is actually a photo of our first prototype. We created a glove that can be placed onto the fingers and actually provides force onto the fingertips in the virtual world. So this is a video of one of my students who has the glove. We created this fun Iron Man game where you need to open up your hand to shoot a laser beam out of your palm to pop some balloons. So the game was focused on the motion of opening those fingers. And then you get a fun sound and you get points for opening your fingers to pop that balloon. If the child is having difficulty opening up those fingers, the glove actually provides a little bit of force on those fingertips to help pry open those fingers. You're probably thinking right now, oh my goodness, what happens if you overextend? We have some safety measures built into the glove to prevent the fingers from overextending. So the goal is over time, as the child is able to open up their fingers, the glove provides less and less assistive force, with the goal of, in the end, the glove provides no force at all, and the child is actually able to open up the hand themselves. So this work is still ongoing. I'd love to answer any questions about this project, and also any questions about biomechanics work, or toilets or otter paws. Group is doing a lot of very interesting topics. So thank you all very much.
All right. Dr. Noel, I see a question in the chat, if you can see that.
Let's see.
It says, how is your past tongue research being used in current or future research?
Excellent question. So a lot of the work with the haptic glove was focused on tendon-based manipulation of the fingers. So we have this tensioning mechanism in strings. We're actually working on using some soft robotic mechanisms in lieu of this tension-based tendon mechanism. So if you're familiar with, it's called a McKibben muscle. It looks kind of like one of those, what are they called? Those cable ties, like Chinese finger traps. It looks like a Chinese finger trap that you fill fluid in or air in, and it's able to stretch and compress and pull. In the soft robotics world, they're used as a mimic for typical, like being able to mimic different types of muscles. So we're looking at how weaving these types of soft robotic muscles, very similar to how some of the tongue structures are, how we can use that for a more lightweight, more responsive method for applying tension onto fingers. And I don't have any photos of that right now, unfortunately.
Oh, excellent. And here's another one. It says, what excites you most about this research?
The biomechanics research or the virtual reality research?
The virtual reality.
I just think it's the future. I mean, it seems very gamified at the moment, but I really do think that the development of virtual reality over the next decade is really going to be a game changer in terms of remote learning, as well as biomedical applications and training. So, I mean, we've all seen in the past almost 2 years now how, changing from in-person to remote has caused us to be using a lot more of these remote communication methods. Well, if you can imagine putting on a virtual reality headset and being able to talk to these people face to face and interact with them and be able to actually touch and manipulate things in this virtual world, we can get closer and closer to be able to, say, do an experiment from clear across the country. And I also think applying a lot of these haptic technologies with this VR training aspect can help with things from helping to train someone on a prosthetic to helping these children develop some muscular control to even doing remote medical procedures. I just think it's a really exciting area.
It is exciting. And Betsy, you may have to ask this question yourself. It is says, when thinking about biomimicry, do you use nature to inspire a new product or technology, or the reverse, and have the problem first and then turn to nature?
That's another really good question. I think it depends on the project and the problem at hand. The work that I've done has been biology first, product second. So we've been very focused on the fundamental research, or asking the question of why does this occur, and seeing how it occurs and seeing how can we actually apply what we've studied to different areas rather than being presented with a problem up front. But I do know that there's a lot of other research groups who go the other way, where they have a problem up front and then they try and combine a whole bunch of different biomechanical principles together to be able to grip onto things. So a really good example is the gecko adhesion, which I think is one of the most popular topics in the biomechanics area. The gecko research was, looking at the fundamental research of how do geckos grip onto surfaces, but has turned into a wide variety of different applications of grip. I mean, you have videos of people using this technology to be able to climb up walls.
Oh, fascinating. So let's do one more question. I see one here. It says, are you working on an actual product to market? If so, what do you think that product will look like, and how long will that take?
That's a really good question as well. You guys are really good with these questions. The haptic glove is still very much in the research phase, and we're really looking at different types of mechanisms to be able to apply tension to a finger from a biomechanics perspective. There's a lot of companies out there that are already developing haptic gloves, so it would be very challenging to compete with them. For example, Facebook has created a glove called, I think it's Haptex. There's a local Atlanta startup called VR Glove, which we have worked with pretty closely, that are also developing a VR glove. But all of these gloves are using a tendon-based system, so we want to be able to explore what's the next step beyond that. In terms of the cat tongue, we are actually still, so we have a patent on the cat tongue grooming technology. We are looking at developing a product in the future that can be used either to help with carpet cleaning technologies and distributing cleansing fluid into challenging carpets, or even being able to Like I said, we had been in discussions with L'Oreal at looking at different types of makeup applicators. So we have been exploring that as well. But we're not yet to the stage of putting a product on the market quite yet.
Well, thank you very much. It's fascinating research, and I have no doubt that we'll see you on television many more times. Thank you so much for being with us.
Thank you all
Alexis.
very much for having me.
It's a pleasure. So that is, everyone, the end of our meeting. For those of you who are on the board, our next meeting will be our board meeting on March 9th. And for those of you, for everyone else, our next meeting will be the annual meeting on May 4th, and hopefully we'll get to be together again by then. Thank you, everyone. The meeting is over. If any of you would like to stay on, I'll keep it open as long as you like. All right. Thank you all. Thank you, Dee Dee, and congratulations to you.
Congrats, Dee Dee.
I'm so excited to have my Sherpa be the ARCS light. That's wonderful, Dee Dee.
It is wonderful.
Congratulations, Dee Dee.
Congrats, Dee Dee.
Congrats, Dee Dee.
Leslie,
Yes, Ellen
I
Adair.
sent you an email.
I got it. I saw that. Thank you
Good.
very much.
So if everybody likes what is there as a draft, it's good to go, I think, just as a follow-on to today's meeting.
Right. And so what we need to do, and ASG is working on this, is get the page for the brand film up so that it links you not to the Dropbox where it currently lives, but to the website. And then as you suggested, it will play on the website. We're trying to work this out, play on the website without
Yes.
going someplace else.
And feel free to amend or edit. I just sort of took a stab at who it should come from. But just
Well,
let me know.
Yeah,
And I will shoot you over something that's appropriate just for corporate sponsors, but I was more interested in something that personalized it from each member.
Great. Yeah, I'll look at it this afternoon. That's wonderful. Thank you so much for
Great.
doing that.
All right.
All right. Well, I'll
Let me
end the
know.
meeting now. All right. Thank
Bye.
you, everyone. Bye-bye.